Well, hello, ladies and gentlemen. It is time for another daily dose of Dorfler. All right. Um, we are now on to section 3, which means that we are coming to an end of our first portion of this chapter in which we're going to have a quiz. So, your quiz, make sure you pay attention to your my plan book and any posts that I do. But the quiz itself is only going to be over sections 2 and 3. The homework assignment you did for section 1, I decided to go ahead and include that into kind of like a review, going over type of situation. So the quiz will be sections 2 and 3. The problem set that will be due on the day of the quiz includes section 1, 2, and 3. So make sure you don't get that confused, okay? Now, in the last video, we talked about net ionic equations, okay? Now we're slightly shifting focus, and we're going to be looking at acids and bases. We've already talked about acids and bases and how they relate to electrolytes and their role in aqueous reactions. Now we're going to dive a little deeper into that. And I'm going to try and just, talk briefly about some of the history of acids and bases and like why they are different, and then kind of go over what is needed, for you to know. Excuse me. Now, when we talk about a new concept that we're going to get into here briefly, I'm going to relate it to something we've already done. Okay, so it's just a shift to the side, but staying on the same plane as what we just did. Anyway, acids. The Swedish physicist and chemist S.A. Arrhenius defined acids as substances that will increase the concentration of hydrogen ions when dissolved in water. Now, the Danish chemists Brønsted and Lowry said that they called them proton donors. Okay, because basically a hydrogen ion is really just a proton, because hydrogen only has one electron, and when you remove that, it's simply just a proton. There are 7 strong acids, like we've mentioned. You want to keep those on the back burner. Bases. Arrhenius, as we just said, he also did bases. He said that bases are substances that will increase the concentration of hydroxide ions when dissolved in water. And then Brønsted and Lowry went ahead and said that they were proton acceptors. Okay, where acids were donors, these bases will be proton acceptors. Okay, in litmus paper tests, you may have done this a long time ago. Bases turn litmus paper blue, acids turn them red. And there are about 8 strong bases. They're soluble metal salts of hydroxide ions that have alkali metals as well as calcium, strontium, and barium. Okay, so now let's talk about this practice one. We're not going to do this practice on the very bottom. We're going to do the sample one here at the top. So we have 3 diagrams, and they represent 3 acids: acid HX, acid HY, and acid HZ. And it's in water, so we know that it's an aqueous solution. We've removed the water molecules out of there so we can only concentrate on the 3 acids here. We need to figure out which ones, or which one or multiple acids will be strong or weak. So we have to look at these diagrams here. Here in the acid HX, we've got acids that are still intact. Again, this is an intact acid molecule, intact. Got a couple of ions here, okay? Here in HY, we have no intact molecules. They are all broken down into their ions. And then HZ, kind of similar to HX, where we have still whole molecules with a couple of positive and negative ions here. So we have to determine, which one is going to be more or less acidic, if you will. Now, in terms of strength, HY, I was really putting some emphasis on this one when we were talking about it, because there's not a single whole molecule left. They are all broken down into their ions for this acid. What does that mean? Well, we knew that strong electrolytes break down into all ions. There are no whole molecules, which means that HY is a strong electrolyte. HX and HZ, they have some dissociation, but not all dissociated molecules are present. So HZ and HX, they are what we call weak acids, therefore weak electrolytes, okay? So HY is the strongest, and HX and HZ, they're probably pretty similar if we look at the number of whole molecules compared to the number of ions present. HZ might be slightly stronger because it's got a couple more that have dissociated, about one more that's dissociated. So if I had to guess, HZ would be a little stronger than HX, but HY is the strongest. Okay. Now we have to identify whether or not a substance is going to be a strong, weak, or non-electrolyte here. So let me get my little pointer. Here we have calcium chloride, nitric acid, ethanol, and formic acid, and potassium hydroxide. Okay, so let's look at these substances. Calcium chloride. Okay, calcium chloride is an ionic substance. Therefore, we should expect it to be a strong electrolyte. Excuse me. Potassium hydroxide is also considered to be a strong or an ionic substance. Yes, it's got hydroxide in there, but it's potassium, so therefore it could be a strong base. Could be considered, people might consider them ionic, but this could also be considered a base. Okay, so strong base or possibly ionic, therefore it's going to be a strong electrolyte. So calcium chloride and potassium hydroxide are strong electrolytes. We have other substances such as nitric acid, ethanol, and formic acid. Nitric acid and formic acid are obviously acids. Nitric acid is a strong acid. It's one of those 7 strong acids. Therefore, it should be a strong electrolyte. Formic acid, it's a weak acid. It's not part of the 7 strong acids. Therefore, it's a weak acid, and therefore, it'll be a weak electrolyte. The remaining compound, ethanol, it's basically a molecular compound. It's neither an acid or a base. Therefore, it's a non-electrolyte. Now, ethanol may be soluble in water, but it will not break down into any ionic components. So, calcium chloride, nitric acid, potassium hydroxide, all strong electrolytes. Formic acid, weak electrolyte. Ethanol, non-electrolyte. Next, for our practice exercise, we are to consider solutions in which 0.1 mole of each of the following compounds is dissolved in 1 liter of water. So we have the identical concentration, which we're going to talk about later in this chapter, identical concentration of each compound in water. Okay, so we've got calcium nitrate, glucose, sodium acetate, and acetic acid. We are to rank these solutions in order of increasing electrical conductivity based on the fact that the greater number of ions in a solution, the greater the conductivity. Okay, so we're going a different route here slightly. So we have to go from weakest or non-electrolyte to the strongest electrolyte based on the number of ions. So let's look through here, okay? We have calcium nitrate, sodium acetate, acetic acid, and glucose. Is there any one of those 4 that we could say, no sirree, Bob? Well, that would be glucose. Okay, glucose is a molecular compound. It's neither an acid nor a base. It can dissolve in water, but it does not dissociate into ions. So, glucose will be our weakest. So I'm just going to write, why is it like that? I want it smaller. Okay. I'm going to call this, I can't even write it on there. So what I'm going to do is going to rank them this way. So we've got glucose as our weakest one. Again, alligator mouth pointing away from it. Next, we have other substances. We've got calcium nitrate. You want to just write these down. I've got sodium acetate. If I can write clearly. NaCH3COO. And we have acetic acid, CH3COOH. Okay. So far, this is our weakest one. Next, we have to look at these three substances. Again, this is calcium nitrate, this is sodium acetate, and this is acetic acid. Well, calcium nitrate and sodium acetate are ionic compounds. Therefore, we should expect them to be strong electrolytes. Acetic acid is an acid, but it's a weak acid. Okay? So we would expect this one, CH3COOH, to be very low on the conductivity. Next, we have our two ionic substances. So when these dissociate, we have to start looking at, how many of each ion will be present. Well, here we're going to have Na plus and CH3COO minus. So we've got 1, 2 ions that it breaks down into. For calcium nitrate, if we look here, we have 1 Ca2 plus, but then we have nitrate that has a subscript of 2 on there. So that breaks into 2 NO3 minuses. So when calcium nitrate breaks down, it actually breaks down to 3 ions, 1 calcium and 2 nitrate. Sodium acetate only breaks down into 2. So that would mean that because sodium acetate has fewer ions, it's going to have a lower conductivity. So NaCH3COO, and our strongest electrolyte, sorry, I got sidetracked there, would be CaNO3 2. So glucose is weakest, followed by acetic acid. Then we get into sodium acetate and calcium nitrate. So that's what it should look like in order of increasing conductivity. Glucose does not break down into any ions. Calcium nitrate does, but it breaks down into more ions for every molecule. So again, we have the same concentration of everything, but this one would be stronger in its conductivity. Okay. All right. Let's get back into this, shall we? Well, I forgot to change the lighting. Sorry about that. Okay, so next and last thing we're going to talk about today is acid-base reactions. We also call these neutralization reactions, okay? And the reason why we call them neutralization reactions is because when an acid and a base react, they form a salt and a water. So they neutralize each other. In an acid-base reaction, the acid is going to donate a proton or a hydrogen ion to the base. And in this situation where we have ammonia and reacting with water in this instance would be more acidic than ammonia. Therefore, the water is actually going to act like an acid and donate a hydrogen to where now we have hydroxides and, ammonium. Okay, but that's not always what happens. Okay, in a neutralization reaction, we are going to start investigating, strong acids, strong bases reacting, strong bases, weak acids, weak bases, and see what happens. Okay, this is just a general statement to what actually happens in an acid-base reaction. Okay, here is what we're going to be focusing on today: is neutralization reactions. When solutions of an acid and a base are combined, the products are a salt and a water. Here we have acetic acid, which again is a weak acid, reacting with sodium hydroxide, which is a strong base, to form sodium acetate, which we just saw, and H2O. Notice liquid. H2O liquid, not aqueous, liquid. So these follow the same rules as a metathesis reaction. They do-si-do. Okay, this hydrogen right here, let's see where my pointer is, left, when it dissociated, now granted, acetic acid is a weak acid, but it can dissociate to an extent. This hydrogen goes off and joins this hydroxide. This sodium goes off and joins this acetate. They do-si-doed. They switched partners. With certain reactions, we can do a net ionization or a net ionic equation, okay? Much like we did in yesterday's video. So here we have hydrochloric acid, one of the 7 strong acids, reacting with sodium hydroxide, a strong base. They do-si-do. They form sodium chloride, a salt, and H2O, a liquid. So then we can follow very similar steps to what we did in the net ionic equation writing, and we dissociate what we can, okay? We can dissociate HCl because it is a strong acid, so they're all dissociate. We can dissociate NaOH because it is a strong base, so it all dissociates. We can also dissociate sodium chloride because it's a soluble ionic substance. What we cannot dissociate, and I mentioned this in the previous video, is we cannot dissociate liquid, okay? Liquid must remain the same. Much like solid remained the same in the past example, liquid remains the same here. So we cross out our spectator ions. Those are things that did not change from beginning to end. And then we rewrite our net ionic equation for neutralization reactions of H plus aqueous plus OH minus aqueous yields H2O liquid. Okay, so there's the gist of it. Let's look at a practice one here. We have a reaction between acetic acid and barium hydroxide. Okay, acetic acid is a weak acid, barium hydroxide is a strong base. We are to write a balanced molecular equation, then complete the ionic equation, and then the net ionic equation. Okay, so right here is the balanced chemical equation. Okay, acetic acid reacting with barium hydroxide will form, again, you do-si-do, H2O, and barium acetate. Okay, barium acetate is going to be an ionic substance, a salt, if you will. So it's all balanced. Well, it's not balanced yet. You have to go and balance it. You then have to write the ionic equation. Again, that's where you dissociate everything. I want to point out something here. You notice how acetic acid is not dissociated into its ions. It's not dissociated into acetate or hydrogen. Okay, that's because acetic acid is not a strong acid. So we do not consider it to be a strong electrolyte, therefore we do not dissociate it. Barium hydroxide, however, is a strong acid or strong base, so we can dissociate that. On the product side, again, we do not dissociate liquid water, but barium acetate being an ionic compound, therefore a strong electrolyte, we can dissociate it. So to finish this out, to do the net ionic equation, we have to cancel out what we can. And I'm going to call, again, something special to this one. You notice that the only thing that doesn't change from the left to the right is barium. Okay, acetic acid, or the acetate ion, was part of an acid here. Now it's an ion here, so it's not the same. Hydroxide is now part of water, so it's not the same. So the only thing that remains the same is barium. So we remove barium. But if you write the net ionic equation, you notice that every single one of those items that remain have a coefficient of 2. Well, we can simplify that even further. We can simplify the coefficients by dividing all of them by 2 and getting our final net ionic equation for this neutralization reaction as we see here. Acetic acid plus OH minus yields H2O liquid plus acetate ions. Okay? Trust me. After this video, I'll be giving you practice. On Monday, I'm going to be on Google Meet to see if you have any questions or would you like me to go over any of the problems before you submit it, okay? All right, let's do our final example, and then we're going to be done for the day. We are to write the reaction for phosphorus acid, which is H3PO3 and potassium hydroxide, and balance it first, and then the net ionic equation, okay? So first I'm going to write down my reactants, H3PO3, that's aqueous, plus KOH, aqueous. So now I need to predict my products here. Okay, I'm going to rewrite this. This marker is just not cutting it. Well, I have to get that. Let's go back to this one, see if I can get this one to work well. Apologize for that. Okay, got the marker that I dropped. Going back into storage. Okay, let's start this over again. We got, come on. Okay, we've got H3PO3 aqueous plus potassium hydroxide aqueous will yield, again, they're going do-si-do. We also know that one of them is going to be H2O, liquid. And our salt here is going to be potassium phosphate, I should say, because we have phosphorus acid. It's actually going to be potassium phosphite. So it's going to be K3PO3, but it is also aqueous. So again, now that we've got our reactants and our products predicted, we have to balance it. And so the balanced chemical equation, we're going to put a 3 in front of the potassium hydroxide and a 3 in front of the H2O, and that should get us where we need to be. Okay, so that is part A. Part B has us breaking these down. Okay, phosphorus acid is not a strong acid, so therefore it does not dissociate. Okay, sorry, I have a habit of putting a period there. Potassium hydroxide is a strong base, so it does dissociate. So again, this coefficient goes with both of these, 3K plus aqueous plus 3OH minus aqueous will yield, again, we don't dissociate liquid water, but we can dissociate potassium phosphite. So you get 3K plus aqueous plus PO3 3 minus aqueous. Again, you're going to need some room here. So next thing we need to do is we need to cancel out what is the same on both sides. Well, H3PO3 is not found on the right side, so that had to change. So we're going to keep that. 3K plus is found on both sides, so that gets crossed out. And 3OH minus is not found on both sides, so it's going to stay the same. So if we are going to write a net ionic equation, we rewrite it keeping what we have left over. So H3PO3 aqueous, I don't know why I do that period at the end, plus 3OH minus aqueous yields 3H2O liquid plus PO3 3 minus aqueous. And that is your answer. That's also why it is very important that you understand and are able to identify strong acids, strong bases, weak bases, okay? Because I was able to identify phosphorus acid as not being a strong acid, I did not dissociate it, and that'll have an impact on your whatchamacallit, your final answer. Okay. So what I'm thinking about doing might be switching a few things up here for your homework that I'm going to post in a separate post to this video. I will probably kind of do another video where I just show you how to do one or two of the examples on the homework. Okay. So be on the lookout for that. If I go ahead and do that, that's just kind of floating up in my noggin right now. So that is actually going to take us to the end. Oh, no, it actually doesn't. So I guess I'm going to talk to you about this. We don't talk a whole lot about this, but just so you know that some of these metathesis reactions don't always give us what products that we would expect to get. Sometimes we can get what are called gas-forming reactions, where we will actually have certain products form liquid water, a salt, and gas, usually CO2. Whenever we have a carbonate or bicarbonate reacting with an acid, it produces salt, carbon dioxide, and water, like I just mentioned. An example of this might be exactly what we just encountered. Last week was Thanksgiving. If you overate or ate some really spicy stuff that didn't quite agree with your stomach and you started getting heartburn, well, you may have popped some Tums or some Rolaids. Those are carbonate and bicarbonate products. Really what heartburn is, it's a buildup of stomach acids to where it goes into your esophagus area and into areas where it's not supposed to be. It causes it to burn. You have an overabundance of stomach acid that has been produced by the food that you ate. So you take one of these Rolaids or Tums, has carbonate or bicarbonates, it reacts with the excess stomach acid, and it reduces it down to where you form water, a salt that can be released out of the body, and carbon dioxide, which is probably why you belch after you take those. Okay, it's not probably, it is why you belch after you take pills like or things like Rolaids and Tums, because it produces when it neutralizes some of the excess stomach acid, it produces CO2, which has to be expelled some way, and belching it is usually the easiest process to do so. Other examples of gas-forming reactions: when sulfite reacts with an acid, we produce salt, sulfur dioxide, and water, but we try not to do that in here because it's very, very stinky. So you better do this in a fume hood if we do it, which we're not going to do. Okay. And that didn't take very long to get to those last couple of slides. Starting next week, we are going to get in what's called oxidation-reduction reactions, or redox. Okay. So, but until then, that is the end of this video. Again, be on the lookout for any additional videos in regards to your homework there may be, but nonetheless, I will be on Google Meets on Monday the 7th during your regular class time to answer any questions you might need. Have a good day.